This video is a complete design guide for medical compressed air systems, focusing on calculations for a 200-bed hospital. We'll cover both medical air for patients and instrument air for tools, which are life-critical utilities under NFPA 99 Category 1. We will focus on the medical air system design, with step-by-step calculations. These systems are Category 1, meaning failure poses significant risks, particularly in operating rooms, ICUs, and NICUs. Our design must adhere to mandatory codes and standards. The primary reference for medical compressed air systems is NFPA 99, specifically the 2021 edition. NFPA 99 Chapter 5 details gas and vacuum systems, classifying hospitals as Category 1 risk. Key sections cover air source, compressor requirements, and alarm systems. We also refer to ISO standards, mandating oil-free compression and redundant sources. Step 1 is the outlet requirements analysis. For a 200-bed hospital, we break down the number of outlets, required flow rate per outlet, and usage pattern for key departments, referencing HTMO 201 data. The analysis shows 200 outlets across departments like operating theaters and general wards, each with specific flow rate demands for calculation. Step 2 is the peak demand calculation. We apply diversity factors from NFPA 99 Annex A, recognizing that not all outlets run simultaneously. Operating theaters are 100%, while general wards are 20%. The total system peak demand, calculated by applying the diversity factor to simultaneous usage, is 3,881 LPM, which is approximately 137 standard cubic feet per minute, or CFM. Step 3 involves compressor selection. NFPA 99 prohibits oil-lubricated compressors. Given our demand, the oil-free rotary screw compressor is our choice, offering high capacity suitable for large hospitals. We must also avoid single compressor systems. Step 4 covers compressor sizing and redundancy. NFPA 99 Category 1 requires N+1 redundancy. We select two 150 CFM oil-free screw compressors, exceeding the 137 CFM peak demand, ensuring 100% backup. Step 5 is receiver tank sizing. The receiver provides buffer storage, stabilizes pressure, and reduces compressor cycling. Based on our flow and pressure drop requirements, we require a 500-gallon, 1,900-liter, ASME-coated, vertical design tank. The calculation using flow, time, and pressure differentials leads to a large volume requirement. We select a 500-gallon ASME receiver to provide adequate buffer storage. Step 6 is dryer selection and sizing. The air quality standard is ISO 8573-1, Class 3.1.1, requiring a dew point of less than or equal to -20 degrees Celsius. We select a heatless desiccant dryer, the standard choice for most hospitals. Step 7 is the dryer sizing calculation. NFPA 99 requires a safety margin. We calculate 360 CFM capacity. We select a 400 CFM heatless desiccant dryer to meet the NFPA requirements, including achieving a less than or equal to -20 degrees Celsius dew point. The standard mandates ISO 8573-1, Class 3.1.1 quality, meaning a dew point of less than or equal to -20 degrees Celsius and low particulate and oil content. The heatless desiccant dryer is the best option for our needs. Applying a safety factor, our required dryer capacity is 360 CFM, leading us to select a 400 CFM heatless desiccant unit. This selection meets all NFPA requirements for dew point and mandatory pre-filtration. Step 8 details the filtration system design, which has 3 stages. Stage 1 is pre-filtration to protect the dryer. Stage 2 is main filtration, using coalescing and activated carbon to remove aerosols and vapors. Stage 3 is point-of-use sterile filtration in critical areas. The minimum filter flow capacity must be 205 CFM. We establish required micron ratings, housing sizes, and element life for each stage. Monitoring using differential pressure gauges is crucial for timely maintenance. Step 10 reviews pressure requirements. The outlet terminal pressure is mandated at 3.8 to 4.2 bars. We implement primary, zone, and local regulators to maintain stable pressure throughout the system, while ensuring the pressure drop is limited. Step 11 involves piping system design. Calculations show that a 1-inch pipe causes excessive pressure drop. A 1¼ pipe is acceptable, but the main header should be 2-inch copper type K for minimum pressure loss. We use type K or L copper with brazed joints. We select a 2-inch main header and 1 1/4-inch minimum branches. The layout will be a loop system with sectional valves for reliability. Step 12 details the alarm system design. The system must have a UPS backup and 30-day logging. There are 3 levels: master alarms at the nurse's station, area alarms in critical zones, and local alarms in the plant room. Step 13 summarizes the system specification. We selected 2x1 50 CFM oil-free compressors, a 500-gallon receiver, and a 400 CFM heatless desiccant dryer. The design ensures 100% redundancy and meets the 137 CFM peak demand. This complete specification ensures the system meets the capacity, pressure, and ISO 8573-1, Class 3.1.1 quality requirements with a rapid switchover time. Step 14 covers validation and commissioning. Mandatory tests include pressure and leak tests, purity testing for dew points and contaminants, and performance checks. Essential documentation must be submitted, including third-party certification. Proper maintenance and quality assurance are vital. We must adhere to strict schedules, including daily checks, monthly alarm tests, and annual filter changes and recertification. All maintenance actions must be logged per NFPA 99. Schedules range from daily checks of pressure and drains, to weekly switchover tests, to a major overhaul every 5 years. In summary, medical air is a drug and must be designed with the same rigor as pharmaceutical systems. Key takeaways emphasize that NFPA 99 Category 1 governs all design decisions. Redundancy is critical, and only oil-free compression is permitted. Independent certification is mandatory before system use. The primary codes and standards include NFPA 99, ISO 7396-1, and ISO 8573-1. Design guides like HTMO 201 provide additional resources. Engineering excellence saves lives. We rely on these codes, guides, and tools for designing reliable medical gas systems. Thank you for watching this professional engineering series video on medical compressed air design.